Okay, so hi everyone, and welcome back to the second lecture of the PCP course. And today we're going to talk about linearity testing. And I even made a subtitle, like in Star Wars, The Empire Comes Back. So today it would be linearity testing and the locality of the Hadamard code. And this is a really, really nice proof. I think it has, it's a very nice idea here. There are two beautiful conceptual ideas, which I really like you to kind of take home and distill because they are beautiful. And about 5 to 6 technical tricks, which will come handy, time and time again. So it's going to be a really fun, though a bit technical lecture. And just to say, in a word, it's the approach that we're going to take as promised to be a research kind of approach. And by that I mean that we'll try to, rather than say this is the problem and here's the solution, we'll try to find it by ourselves, and we'll get stuck. And whenever we get stuck, we'll kind of get some hint or another idea, but it will be a process of discovery as opposed to just being laid with some solutions. Okay, so let's dive right into it. So first of all, recall that we, on the last episode of the PCP course, we discussed about this notion of proofs and probabilistically checking them, and we said that the meat and potatoes, the technical tool which allows us to have this magical proof that you can check locally is local to global phenomena, which is what allows us to take some local property and make it global and pronounced in the entire object. And we gave this example of the jam principle, where maybe you have a piece of bread, you want to get to taste the jam, but it's concentrated, so you spread it uniformly, and then it doesn't matter when you take your bite. We define the notion of probabilistically checkable proofs as an NP proof that you only probe locally at maybe 3 locations and then you verify it. And finally, we said that there would be these 2 underlying leitmotifs of one of property testing, which are problems that we can do very locally, and by deciding whether an object has a property or whether it is epsilon far from it in some metric. And the other one which would complement it would be that of coding theory, which is where we take arbitrary data and we endow it with symmetry and nice properties, such that every pair of objects would be very far from each other, and they would have symmetry and nice properties. Okay, so the problem that we're going to do to deal with today is that of linearity testing. And as the name suggests, this is an instance of property testing. So let's discuss the problem. So we have a function f taken over some finite field f. And it's a function in n variables, 2f. And we say that the function is linear. Well, if we can just write the function as a linear combination of the variables. Right, so I'm not telling you here anything exciting. Function is linear if it's linear. Right, if you can just write it as linear terms. Okay, nice and well. And recall the problem that we'll be interested is, we'll have the class of all functions, which we're getting, and we'll get one function from the class of all functions. And in this class of all functions, there are the linear functions. We might have your quadratic functions and then functions of higher degree, but these are the linear functions. And in some sense, we want to know whether we're linear or whether we're not linear. Okay, so first observation that we can ask ourselves is, what is the proportion of all functions and linear functions? So can anyone tell me how many functions we have on a finite field? Suppose that you have this finite field of size, size of f, and it's in n variables. So what is the total number of functions that you can define?
F to the n? No.
Exactly. So f to the n, right? I mean, so Philip is writing 2 to the 2 to the n, and that's correct if f is 0, 1, if it's like f2, but f could be of arbitrary size, so the size of all function, it's like f to the f to the f. Why? Because we have a truth table of size f to the n, and we can choose, we have f options for each one of the indices. So we have f options for the first value of the hypercube and f options for the second value of, and so on and so forth. Okay, this is nice and well. And how many linear functions do we have?
F to the n.
F to the n.
Exactly. Excellent. Right, and the idea is because what is a linear function? I mean, we have n variables to choose from, and each variable can get one coefficient from from the field f. So we have f choices for the first coefficient, f choices for the second one, and so on and so forth. So what does this tell us? It tells us that the class of functions which are linear is extremely small. It's exponentially small in the size of all functions. So it's a very sparse and structured subsets of all functions. And by the way, as I said that, I will keep hinting to coding theory. So the class of all linear functions is often referred to as the Hadamard code. And this is a code which adds exponential amount of redundancy precisely because of this reason. Because you say, I take one linear function, and then I will represent it by I will have a concise representation for it out of all functions. But we'll get into that in a more concrete way. So don't mind if this was a bit confusing. Okay. So what we want to do is we want to have this extremely local test that maybe we'll make 3 queries, maybe we'll make 10 queries. But the idea is that we'll make a very small number, constant number of queries. We'll only evaluate the function, f at 0, 0, 0, f at 0, 0, 0, 2, and f at 7, 1, 3. Just like 3 locations, and still be able to say whether the function is linear or not. So that's a very ambitious goal, but it's also an impossible goal. Because what happens if you have a function? And again, the thing about the function, you're given this truth table. So you allow to query it, you give an x and you get back f of x. So it could be the case that you have a function which is completely linear, and then you just chose one bad place where you kind of flip the value. So it's a linear function except in one place. And then, you can never find it unless you query the entire thing. So this is why we're doing the property testing relaxation, where the idea would be that if the function is linear, we will always say yes. And if the function is epsilon far from being linear, then we will say no. And what do I mean exactly by far? So we'll do this counting in Hamming distance. And you might ask, typically Hamming distance refers to zeros and one, but but we're working on finite fields. So this would just be the fractional distance, right? So nothing fancy at all. It just means that I look at all of the values of x and g, and I count how many x's on which f and g are not are disagreeing. And similarly, when I say the distance of a function from a set, it would be the distance of all functions within that set. Okay, so what does it mean to be a linear function? It means that if I evaluate a function in all places, I get this linear function. And if I'm far from it, it means that I need to change a certain fraction of the truth table in order to make the function to become linear. Okay, nice and well. And we'll now try to solve the relaxed question, the problem. We know that we can't solve the exact problem, but the idea would be, can we solve the relaxed problem? So is the statement of the problem, does it make sense? Is that clear?
Sorry, what is S here again?
So S here is just like an arbitrary set. So I just try to say what I mean by the distance from a set. So in this setting, the set I care about would be lin, like the set of all linear functions. And so I mean that the distance from the set of linear functions means, out of all elements of the linear set, which one of them I'm closest to. Okay, Good.
Sorry. Can the field be infinite?
So we are dealing only with finite field.
Okay. But then I'm confused where it says this is impossible, because it is possible, right?
To do it exactly while only looking at constant number.
Oh, you're right. Yeah.
That's the point. If I only allowed to look at 3 values, then I can't know for sure, because there is always a value. Okay.
I don't really understand the definition of the Hamming instance between 2 functions.
Yes.
It's a probability.
Okay. So that's a good question. Thank you for. It's just like it's an abuse of the notion of probability just for the sake of counting. So what I want you to have in mind is, we have a vector, f of 1, f of 2, f of 3. Like you evaluate, it's a finite field, so there are just a bunch of locations where you can evaluate f. And similarly, you might have another function g, well, g of 1, g of 2, g of 3. And now what would be the Hamming distance here? It would just be what is the fraction of inputs, what is the fractions of coordinate of like x's on which these functions disagree. So for example, if this is like 1, 0, 1, and this is 1, 1, 1, then like the fraction of places where they disagree is 1/3. And it also means that like if you pick one coordinate at random, then the probability that they differ would be 1/3. So we're using the probability just as a convenient notation for counting. Okay. So now I want to ask you, before we're getting a solution, how on earth are we going to attack it? So if you already know the solution, then please don't say it. But if you don't, I'm curious to see how one might approach it. And while you're thinking, let me muse for a second about why, at least at first, this seems like a hard problem. And the reason why it seems to me like a hard problem, this it did the first time I looked at it, is that what we want to find out is this condition of linearity. And we only get like to evaluate the function that it's a small number of places. Now, suppose I'm getting, suppose I want to understand whether this is a linear function or not, then I need to kind of like figure out what are the coefficients. And if I only get 100 queries, then it seems like this is a very global property, right? I mean, it's like really one has to figure out and deduce the coefficients. And so, if I was presented with the first time, I would be kind of hesitant regarding that one can even get any meaningful information. So quickly going over the questions in the chat, we'll see exactly how far is far, but the good thing to keep in mind is kind of like, think about the constant, like 1/100, but we'll see exactly how this relates. And another question that I see is how we represent the function. So we represent the function exactly with the truth table. So think about it as a vector of evaluation of the functions over the entire domain. Okay, and I see that somebody already gave a fantastic answer, which is actually a big idea that I like a lot. So well done. And let me kind of present this idea. And it's a really important phenomenon in mathematics in general, and that's this important concept of duality. You know how when we first learn linear algebra, we're kind of like saying you have a matrix, and the matrix, it's a grid of numbers, but you can also think about it as these, representing the coefficients of equations. And you can also think about them as linear transformations. And you can also think about them as linear subspaces, right? So we have one object and we have several different of equivalent perspectives to look at it. Now we might say, well, it's all the same, and you'd be 100% right. But by viewing the object in the right perspective, it sometimes allows us to do things which otherwise, we wouldn't feel that we can do. So I want to tell you about this absolute protagonist of this lecture, which is an object that I like a lot. This is a triangle. And a triangle, I have to say, I really love triangles. they're cooler when they're in higher dimensions, but they're simplices, or maybe that they come in a simplicial complex. But even when we look at the single triangle in 2 dimensions, then it has a nice property that it captures linearity. This x and y equals x plus y, and inspired by that, I can say, sure, a function is linear if you can write it as a linear combination of the variables. But you can also use the dual perspective and say that, a function is linear if it is behaving as a linear map. And that is, if you take f of x plus y, then it's just equal f of x plus f of y, right? And the beauty about this is that that's a very local condition. Right, whereas before we have this, like the first condition, it talks about the entire structure of the function. Here we have a condition that you can say, well, I can just look at x, y, and x plus y, and I'm getting some information. So this is an important idea, and you'll see it appears many, many times, despite how trivial it is. We'll want to see whether the global functions that we have admit these local constraints that express them, right? So, and this is say, if we want to test, to decide to solve the exact problem, is this linear or not? Then it means that instead of reading all the values and checking whether it's consistent with some linear function, we can just go over all possible triplets and see, whether each time we choose x and y, it would satisfy the linearity condition. But when we're looking now at the relaxed setting, you might say, well, here's a naive idea. Let's just choose x at random. Let's choose y at random, and check that, f of x plus f of y is f of x plus y. And maybe, if this is a function which is linear, then we know for sure that this would hold. And maybe if this function is far from linear, then here we might have some problems. Okay, so I'm skimming some questions. So when I'm saying a triangle, I hope I don't confuse. All I mean is just a triplet of x, y, and x plus y. So that's the whole thing, and I'll care about them satisfying, this crucial condition. And I'm not sure regarding the question of scaling, because we are now in finite fields, so everything is kind of like a modulo type of arithmetic, but feel free to elaborate on that more. So in the meanwhile, I just want to say, so this is the idea, and let's try to actually build something. So we have the linearity test due to Blum-Luby and Rubinfeld. It's often being referred to as BLR. So if you hear somebody talking about the BLR test, then that's exactly that. And the idea is exactly what we kind of figured out together, which is what the test is going to be. So it's an algorithm that gets an oracle access to the truth table of a function. And what we'll do is we'll sample at random some x, some y, and we'll check that f of x plus f of y is f of x plus y. It's as simple as it could be. And what would it cost us? It's 3 queries to x, y, and x plus y. And in terms of randomness, we need to kind of take at random x and take at random y. Okay, so I see the question of Wilfred. So yeah, I see what you mean by scaling, but in fact, it's just suffices for us. It would just suffice to just look at the simple setting of fx plus fy in this. I think that the reason we first looked at it is because this was first analyzed in the setting of the hypercube, where scaling doesn't matter, but this is definitely a condition which suffices for linearity testing. Regarding Ili's questions, so the Blum-Luby-Rubinfeld test is exactly the test that I presented now. And duality is just this notion that we can, it's a general notion of mathematics that we have several equivalent representation of the same object. Okay.
Tom?
Yes.
Maybe I missed something, but when the field is not of prime size, we had this discussion, then this is not enough for the regular notion of linearity, right? It's just being a homomorphism as an abelian group. which is a weaker notion.
Yes, so I guess that okay. So I think that what could be the most helpful is first to think here about the problem as maybe just a prime field. It would be much easier to kind of digest it. And we can later see exactly what changes while we consider general finite fields. Okay, and keep that in mind while you're going through it. Okay, so I want to say, so we have this test, and now we want to analyze it. So first of all, completeness, and that's going to be a trend. Completeness is completely trivial. What do I mean by completeness is trivial? If a function is linear, then, well, for every pair of x and y, we'll have that f of x plus f of y is, is equal to f of x plus y. So that's like the trivial part of things. And this would be a motif in property testing. Like we'll design these tests. And if everything is okay, if the function has the property, then it would be really easy to check it. And the one place where we'll have to sweat a little bit is exactly when we're trying to analyze the soundness. So what is soundness? It means what happens when a function is epsilon far from being linear. So the name of the game, what we'll try to prove is that if the function is far from linear, then our algorithm rejects. Or in other words, or more precisely here, what we show is that the probability that this test will reject is at least the minimum between some constant and this other term. So I want to first encourage you to completely ignore the constant. This is kind of like not the point. That's the main term. So maybe like what I kind of want to say is that we want to say that the probability that we will reject is kind of a good, closely related to the distance of the function from being linear. So I want to say before we stare a bit at this theorem first, like what is the intuition? The intuition, I kind of want to say that the number of bad triangles, so bad triangles would be triangle like x plus y that doesn't equal to f of x plus y. So I want to say that this number of like triplets, which doesn't satisfy the linearity condition, is kind of a good proxy for the distance of f from the being linear, right? So like, and this is a nice robust condition. It tells us that, yeah, if my function is really far from linear, then there would be a lot of triplets that don't satisfy linearity condition. And otherwise, it would be good. And what we actually get is almost that. So essentially what we have is, let me just clear it a bit. I can only do this undo. Okay. So what we're getting is the probability that we will reject, which is exactly the same as the number of bad triangles. It's, at least half times the distance from f being linear. And we also have this annoying constant of 6, which kind of like says that there is some cap. Like if the function is like really, really, really far, then we still won't do better than reject with probability 1/6. So that's kind of the setting of the theorem that we are about to prove. And we're going to kind of spend the entire lecture proving this theorem. So, if you have any questions regarding the statement or the problem, now is a great time to do so.
You just said if the function is really far, but did you mean if the function is really close? Because if the function is really close, then it's more likely that we're gonna fail. Or did
I think maybe the directions are reversed. So let's see. But what are we saying? We're saying, suppose that the function is extremely far. So let's say, the function is maybe, I don't know, 1/8 far from being linear. Then it means that the probability that we will reject would be, 1/16. And if it was, less far, it was, something like that, then this would have been, if it was like even closer, then it would be this way. So like the better, like the farther you are from being a linear function, the easiest it would be. Because think about it in the non-computational setting, like this, even though it refers to a probability of a randomized algorithm, the algorithm just does, like, it's just doing this test. So it's just like saying, the farther you are from linear, the more triplets of x, y, and x plus y that doesn't satisfy this constraint. Okay, so let's try to think, I mean, how do we start, right? I mean, suppose that we're getting that as a research problem, and we need to kind of understand what's going on, right? So we already had one big conceptual idea, and that was like this notion of duality. And here there is another big idea. And the big idea is local correction. So what do I mean by local correction? If you notice, this condition, it actually admits something, something nice. So what is this nice something? Well, so suppose that you have a function, and the function is linear, then it tells us that we can always infer the values of a function by looking at some random neighbors. So let me say exactly what that means, because it's a really important and easy idea. So first of all, the equation that is written here, it's it's just like the linear equation where we moved around one term. But it tells me that suppose I want to know what is the values of f at point x. So I don't really need to look at x at all. It suffices to choose any point that I'd like y, and then I choose, f of x plus y, and I read the value. I choose f of y, and I read the value, and I subtract these two things, and I get my value x. So in some sense, it gives me that if I want to recover the value of f at point x, I can do it by talking about like 2 to the n different values. I can always choose some, vector y and do this trick. So this is exactly this local to global phenomenon. It's like the symmetry that we discussed. It means that every point, in fact, is being written everywhere. And we'll exactly capitalize on that. So what can we do? So the point is that, even if we have a function which is not linear, but it's somewhat close to it, we can still try to see, can we correct it and make it a linear function? So here's an idea. It's a very, very long notation for a trivial thing. So let me first say what this thing is. So I'm going to define this function, g of f. And what is this function? This function, it's kind of like, you can think about it as a voting scheme. So what does it mean? I want to know what is the value at place x. So I'm doing this local correction according to all possible neighbors y. And I'm checking out of all of these y's, what is the most common value that I'm getting. So I have this like f of x, I want to know what is the value. So I'm, looking at f of x plus y minus f of y for all possible y's. Each one of them would give me a certain, value. And then I'm choosing the one which is the most common. This is called the plurality vote. And so this is like a big idea, this notion of correction. And we'll see exactly why this is useful. So let me kind of like say how we can use this idea in order to prove the theorem that we want. So the idea would be, well, first of all, notice that we want to argue. We want to show that the rejection probability is close to the distance from linear functions. But linear functions, it's a complex set, and it's hard to argue about it. What could make our life much easier in a technical sense is if instead of talking about all linear functions, let's just fix one linear function. So suppose we can find one nice linear function, and we can show that, the probability that we reject is like the distance of our function to that particular linear function. Then it also means, it's a special case of being far from the state from all linear functions. So we're making the problem easier but instead of talking about the distance from all linear functions to just one linear function. And now you might ask which linear function we need to check. And maybe a good idea would be to get the function that we get by correcting our function, by making our function linear, by looking at this plurality vote. So that's like a really nice idea. And when I'm saying it at this resolution, it might be a little bit vague. And so we'll have another round of proof intuition or proof overview, which will hopefully make it extremely concrete what we're trying to do. So let's dive right into it. So here's the idea that we'll try to do. So first of all, recall we have this test which just choose a random x, y, and check this condition. And we want to prove this theorem. And this is just for us to remember what is the definition of the plurality vote. Okay, so before I start, any questions regarding the definition of the plurality vote? Okay, I see from your faces that
Short question. So if f is linear, then g of x is equal to f of x, right?
So this is if f is linear, then g of f is equal to f. Yes, exactly.
Okay.
And in some sense, it means that like if you have a linear function and you try to correct it to a linear function, then you just remain exactly yourself. Yes, that's a good question. Okay, so I want to show you what is the strategy, which is kind of like a straightforward implementation of what we said, but just in a formal way. So the first step would be to show that the number of bad triangles is being captured by the distance of our function from the plurality vote. So let's digest this for a second, so it won't, be confusing. So what I was saying, so the number of bad triangles, this is exactly the probability that we reject because we're just checking a random one. And we'll kind of show that this is lower bounded by half of the distance from f to g of f. So, let's not think too much about this half. It's not, very important. It kind of tells us that the number of bad triangles is roughly the distance of a function from its, correction, from its self-correction, from the plurality vote. So this step is exactly the step that tells us, instead of, checking the distance of f from the set of all functions, let's just check the distance of f from one particular function. And you'll see that the way that we chose g of f is exactly so it would be really easy. This is like a two-line proof to have this connection. And we'll see it in like 2 minutes from now. Okay, so that's the first step. And now I'm going to skip one technical step and go to the final step, which is step number 3. And you'll see in a second why I'm doing it in this order. And what we want to do here, all we want to say here is that the plurality vote, like this function g of f that we have here, is in fact a linear function, right? I mean, so we have, so what does exactly does it mean? We define this function where we take the value of each point by by looking at the majority, at the plurality of all triplets that would lead to correcting each value. And what we'll actually show is that if the function, if we don't have too many bad bad triangles to begin with, then this correction will work nicely and the function will be entirely linear. So it means that, and this is not something that is trivial, that by going with the plurality vote, it would actually give us a linear function, but we'll actually show that. So let's see what we have. So first, we know that the rejection probability of our algorithm is pretty much the distance of f from gf, which we define from the plurality vote. And we also know now that the plurality vote is a linear function. And so it means that the distance is exactly that. And we get this annoying factor of 1/6 because we need it here for the plurality, for this condition to hold. Otherwise, we have a problem here. And the reason, the intuition why we need this thing is because if the function is completely far from being linear, and it's like just random bunch of points, then it would make very little sense to try to self-correct it because it's just like noise. But you see it all being done, in more detail in 2 minutes, so we can dive into that right then. And the missing step, which is a technical step, is somewhat surprising. This is the most magical part of the proof for me, because if I had to bet and put my money, then when I first saw this proof, I wouldn't necessarily think that this holds. This is like a magical property, a really nice property of linear function. And it tells us that plurality implies overwhelming majority. So what do I mean by that? So what we did here with this G of F, we said, let's look at the most popular vote, right? So suppose that the values are kind of like, it could be only 0 or 1. So, we'll check whether the most of the values would give us a triplet that leads to 0 or to 1. But it could be the case that we'll get like half-half or something which is very close to it. And what we actually show that if we rule according to the most popular vote, then in fact this vote would be an overwhelming majority. It would be like a 2/3 majority. So being more precise about it, we'll show that, this is the probability that a triplet would correct. So this is G of F, which is like the most popular value. And we're saying on how many of like the triplets this would happen. And we'll get this expression, 1 minus twice the number of bad triangles. And because we have this condition of 1/6, then, so this number is, at most 1/6. So this entire thing becomes 2/3. Right? So what happens here? It tells us that, we define this function, which is the most popular vote. And by the conditions, by the structure of linearities, it tells us that this actually means that we are not only going with the most popular vote, but like one vote should be really, really, really overwhelmingly supported by all of the triangles. Okay.
Tom?
Yes.
Looks like, to me at least, step 1 and 3 imply the theorem, or are you using step 2 as a claim to prove something
So
else?
step 2 is just a technical stage. Thank you for asking that. It's just like a technical stage for proving step 3. And the moment that you have 1 and 3, then that's enough. But it's like a really important step, so which is why I kind of like made it an independent thing. And what we'll do now is we'll just go claim by claim and prove it. And you'll see that the proof is very, very simple, but it has quite a few gems in it, in the sense that there are these nice technical tricks that are extremely useful and will repeat, time and time again. So it's really worth doing it. I will also say another thing before we start with the proof itself, is that the lecture tomorrow will do this like low degree testing, which would be a much, more sophisticated and beautiful construction, but the skeleton of the proof would be exactly the same. We'll start with this, we'll want to check low degree polynomials, and we'll have this like duality, like other ways of characterizing low degree polynomials. And then we can check which is like local, and then we check this local constraint, and we'll have this exact 3 same steps. So that's a good thing. First, because if you got it right now, then you're like definitely in a good shape for tomorrow. And if you don't fully grasp it, then you'll have another chance, another iteration of doing it in a different setting, which can help understand it. Okay, so obviously,
sorry, one more question. Is step, if I understand correctly, you're saying the claim in step 2 is correct for f's that are somehow far from being linear?
I'm saying,
or close, sorry. Like, does the second claim hold for any f?
So the point is that no, it is it holds for every f, but without this statement. Like this would hold only our assumption here of the 1/6. So maybe it's better to kind of like write this in a different color. And this is just like for our parameters.
And
But the statement that holds is 1 minus 2 times the probability of like having this 0.
but okay, so it seems that this like I'm trying to think what I mean. This probability is some sort of property of the protocol. I'm trying to understand what does it mean for F?
So it's a fantastic question. So I want to say, recall that what is this probability that we're talking about? It's a protocol, but what is the protocol doing? So you can see here up, it checks this condition for a random pair. So this probability is exactly the number of triplets x, y, x plus y, such that this condition doesn't hold.
So maybe one way.
Combinatorial measure.
Yeah, so it's like the distance from being linear when I measure by triangles. Or
exactly. That's a beautiful way of putting it, right? Because like what we're trying to do is we care about Hamming distance, but we're showing that the linearity constraint distance is a good proxy for the Hamming distance. Yeah, this is exactly what we're doing. Good, excellent question.
I have a question. So in the theorem, you have minimum, you take the minimum distance of f from the set of all linear functions.
Yes.
But then you say that instead of considering the set of all linear functions, we can just consider this plurality function gf.
Yes.
But you also need to prove that this gf is the best function in the set of all linear functions to take, right?
No, I need to show that gf is a linear function. And then I'm showing that there exists one linear function from which, okay, so I see that, okay, see that, maybe I said it in a confusing way. I mean, we want to say that the probability of rejection is larger from the distance of f from all linear functions. If we are given one particular linear function, then, you know, this distance is the distance from all linear function. So it might be that gf is not like the closest function. It's not the closest function, but it is a lower bound for everything, right? It's confusing the directions. Like one has to be really careful. So let me just like say it again. So, you know, we were saying that we are far from linear function is f is far from each one of the function inside them. Now we are showing this statement. We're showing that we will reject with probability of the distance from one particular function. And this is also a lower bound in the distance between all functions, because definitionally it means what's your different from all functions, in particular from gf. And it might require like to write it down by yourself to fully see, but yeah. Any other questions before we start? Okay. So let's do it. So here's the analysis. Just remember, I'm writing here just for your so to remember, and we want to say that if this g of f, this plurality vote, is far from the function, then we reject with high probability. So how do we do that? Right. So just like restating the claim. So what I'm going to do is I'm going to define this set S of bed triangles. So what do I mean exactly by set of bed triangles? I'm saying let's consider all of the points X such that if I try to correct them, then most of neighbors Y would lead me to the wrong outcome. Right? So in some sense, this is like a way of saying this means that any element in this particular set is a place where g of f will differ from f. Right? So what are we trying to do here? We're trying to say we're trying to say that the number of bad triangles is kind of like lower bound by this number. And in order to do so, we say, let's look at particular type of points that would lead us to reject. So let me kind of like go to the next step, and maybe it would be easier to see. So we start by looking at this, probability of rejection or number of bad triangles. And we're saying, if I'm in the set S, then my life is somewhat easy, because this condition immediately corresponds to the definition of G of X, so I will have an easy time. And what we'll argue is that if it's not in S, then we don't care, because it's not like we have enough mass. So what do I mean by that? We're doing this condition. So this is just conditional probability. So we're saying, this is the case. Suppose that X is in S, then what is the probability that we will reject conditioned on S being in S? And suppose otherwise, and what would be the probability that we'll reject them? And in some sense, we're kind of going to ignore this, right? So we say, we want a lower bound. So maybe even if you're not in this bad set S, you'd still reject, but I don't want to worry about it. I'm happy just proceeding with this thing. And this means that, I'm narrowing down my set of bad points to those which just belong in S. And then maybe my life would be easier. So what's happening? So here we have this simple situation where we say, first of all, what is the probability of X being in S? So, we choose uniformly. So it's just this is exactly as was asked before. This is where we use probability as a way of counting. So the total number of points is F to the N. And we say that the probability of checking, because we're doing uniformly, it's just S divided by the total number of points. And then what is the probability that we will reject, assuming that S is in that set? Well, that's precisely half by the definition, right? Because if you see, oops, just 1 second, not what I wanted to do. Okay, sorry for that. Okay, we are here. So the reason why we chose S to be this particular set is because we know that if we're in S, then half of the corrections, half of the votes would cause us to reject. Okay, and so what we are getting here is, we can safely discard this. This becomes the 0 here. And this is just saying this is a large enough set. And here we get definitionally that the probability of rejection is a half. Okay, so what happens now is we just need a minor observation, which says that suppose we have some X, which is not in the set S. So if this is the case, so definitionally, it means that this condition holds for at least half of the locations. And so we have that f of X is equal to G of F, to the correction. So what does it all mean? Let's summarize that. It just tells us that we can lower bound, maybe I shouldn't use so much notations. Okay, so we can lower bound S over F by the distance of GF from F. Okay, so what is happening? Let me kind of just say it again, and then I'll answer some questions. So, so what all that is going on here is we're saying, we have an easy to analyze set. And we're saying, in order to bound the probability, it suffices to, we can look under the condition that we're inside or outside. Because this set is large, we'll just focus on the set S and we'll discard everything else. And finally, the probability of rejection while we're inside the set is, as we defined it, exactly half. So we get this number. And then to finish the proof, we just need to tie this number to this number. But the point is that we know that if we are not in S, then we have an agreement. So it exactly means that the size of S bounds the distance of G from F. So that's the entire idea here. And that's, it's just a fairly standard way of zooming in on what we care by choosing a particular set. Okay, I see there was a question, but it was answered in the chat. Thank you for helping with that. Okay, any other questions regarding that proof?
Yeah, maybe stupid one. Why don't we have equality at the end, or do we?
Once again.
Last line.
The last line. That's a good question. It does seem, I see your point, but maybe there could be. I mean, we definitely have a lower bound. Trying to see if there could be a way.
No, don't bother much if.
No. I think it might be inequality, but let me think about it and get back to you offline just to make sure.
I think it might be an inequality because you can still have an X in S where you still agree with F. Like F may not be the majority, like the gross equals a half, but it still could be a majority.
Yeah, fantastic. Thank you, Wilfred. That's exactly that. Good. Okay, so now we can continue with with the second part. What is the second part? We wanted to show that that the plurality vote, like the most common vote, actually implies an overwhelming majority. And again, maybe I shouldn't have written the 2/3 here. This is only assuming that we have this bound on on that bound of projection of distance 1/6. But so we want to say that the plurality implies this overwhelming majority. So let's see how we can do that, right? We want to analyze this this expression, and one trick which always so here there's a bunch of nice tricks. So let's kind of do them one by one. So first thing, we start by doing nothing, just changing our notation so things would be easier. So what am I saying here? So remember that we're saying this is the probability. This is not probability. This is the plurality vote, and that's what all of the possible corrections with respect to y. So now I want to write it in a different way. So a different way of writing it is to say, what are all of the possible votes, and let's see over y to which they would lead, right? So this is an entirely just writing thing in a similar way. GF is the most common vote, and here I'm writing the most common vote by saying, out of all possible votes, which one gets most of them. So I did absolutely nothing, just changing notation. But why did I change this notation? Because it allows me to do a trick which we do all of the time, which is to move from L infinity to norm to the L2 norm. So this is a trick that's being done all the time in functional analysis. And let me kind of spell it out explicitly. So what does it mean? It means that suppose that I want to analyze this sum, just any pi squared sum of I over pi squared. So, it's a sum of pi times pi. And because I can always choose the biggest bi's of them all and take the maximum and maintain the rest of the sum, and I still get this inequality, right? Instead of having p1 times p1, p2 times p2, and so forth, I just take the biggest, p max, and I do p max times p1, p max times p2. Okay, and why would I want to do that? Why do I want to move from the L infinity norm, maximum, and move into the L squared norm to deal with the L2 norm, to deal with squares? Is because this actually expression, it represents a very natural quantity which is easy to analyze. And what's that quantity? It's what we like to call the probability of collision. So what do I mean probability of collision? So let's do it slowly so it would be clear. So I'm looking at f of x and f of x, and I'm choosing two different neighbors. One of them would be y, and one of them would be z, right? So both of these things, so I take this term, and I'm getting some vote for f of x, and I'm taking this term, and I'm getting some vote for f of x. So this is telling me what is the probability that if I'm taking two random votes, that they would just happen to agree, right? And why does this hold? So this is just rewriting it, right? I mean, here I have a probability of V being equal to something times V being equal to something, which is mean exactly what's the probability if I'm taking two IID votes, they would be the same, right? So this is a collision probability. It's kind of like, it takes time to see it properly, but it's like completely straightforward. And the nice thing about it is that we have lots of tools of understanding this type of collisions. It's like you have in birthday paradox, where you want to know what is the probability that two people in this room would have birthday at the same date. It's exactly this type of idea where we're saying, what's the probability of two self-corrections to lead to the same value? Okay. And now essentially, assuming I can bound this probability, then we're happy. So does this as a strategy for proving this claim, does it make sense? Any questions?
Can you explain how you remove the summation?
How do I, because what is happening here? Yeah, so think about this as maybe, summation over PI times PI, right? It tells you what is the probability that both of the votes give you 1? What is the probability that both of the votes will give you 2? What's the probability that both of the votes will give you 3? And that's exactly the sum of all of these collisions. This exactly explains what's the probability that there would be a collision. Thanks. Okay, so now we reduce the problem into just understanding this quantity, and we can do tricks that we know and exist in the literature quite a lot. So I want to show this following claim. It looks maybe intimidating because of the notation, but it's actually, what it tells us, that this collision probability, exactly this thing here, is bounded by that quantity that we want to prove to begin with, right? So assuming I prove this claim, then automatically we've concluded the proof and we can say, yes, we're done. So this just means that we need to show this claim and we're done. Just what is the probability of seeing a collision? And how do we do that? Okay, so, if you just, I'm defining a set here, and you might ask why, right? It looks like such a long and cumbersome definition, and it's a bit intimidating, right? So I want to show you how one can approach the proof such a statement. So we want to show a collision. So what I want to do is I want to highlight one particular set that it's easy for me to see that collisions happen. And now look at this condition. I have here f of z, and I have here f of z. This is not a coincidence. I have here f of xz, fx of z, x plus z, sorry, and I have here f of x plus z. Now, suppose I just plug in this equation. So let me just do it explicitly. Suppose I take this one, and I plug it here. And I take this thing and I plug it here, then terms will cancel out and I get equality. So what does it mean? In other words, this set T is a set of points that if I take a pair xy in T, then I have a collision. It is a sufficient condition for collision. So remember how in the last slide we had this set S, which was a sufficient condition for finding a violation, and it was easier to analyze? It's the same trick. We find some particular structured set of pairs of points that admit a collision, and we just argue about that. So here are the two observations. It's just a two-line proof. So the first thing is that we're saying, well, if we are in T, then exactly as we said, it means that we can write this equation, and the terms just end up canceling each other, and we get a collision. So this is just this is how we chose it. And now let's try to think what that actually means. It means that, if you're in T, then you have a collision. So now we want to give some lower bound on what is the probability of having a collision. So let's just bound what is the probability that we are not in T. So if we are not in T, then we might not have a collision. And if you can say that everything outside of T is kind of small, then we're happy. So what we do is we say, well, what is the probability of us being in T? So if you think about it, what do we have here? We're taking, X and Y, and this are randomly chosen, and this is randomly chosen. So each one of them is just like a random triangle. So it's just the probability of having two random triangles that are bad. And that's exactly what we wanted. Okay, so that's conclude that, and that's like one of the trickiest part of the proof. And now all we have to do is prove one easy claim and get into like an interesting digest and then some, I think, nice insight we can take from it. So any questions regarding this trickiest part of the proof?
One question. In your set T, how is the X defined?
So the set T is, okay, this is a good question. I should have said, like, we want to fix an X that we care about, and for that X to argue about the set T.
So the set T is parameterized over X, right? For each X, you will have a different set T.
Yes, exactly. Thank you for pointing this out.
Okay.
Okay, so now let's kind of like prove the last thing that we need. So we remember that what we've done, so we want to prove this theorem, right? Like that the rejection probability or the number of bad like triangles is the minimum between a sixth and the distance, half the distance from F to being linear. We had this correction function, and we proved, first of all, that like the quantity we care about, the rejection probability, is at least the distance from this particular correction function. And we also show that this function, like the number of linear constraints that it satisfies, number of triangles is like 1 minus 2 to the rejected, something that will later be 2/3. So, the plurality vote is in fact a vast majority vote. So the point is that, if this number is greater than 6, then we are done. But why are we done? Because remember, what we want to prove is this statement, right? So if this holds, then we are done in a trivial way. And in some sense, if you're again trying to, try to understand how people came up with this proof, then in fact, this is reverse engineered. It's not that like, if it's greater than 6, then we're happy, but rather we try to prove this in general. We can't. And so we're kind of like weakening the statement, and we're saying, well, we can't deal with that case, so let's just like stick it here inside and leave it for future work to improve on that. Okay, so this is like how these things actually, I imagine that how they work. Okay, so this means that we're in a good situation now. We can assume that the function is, like the number of bad triangles is not too large. It's bounded by 1/6. And if we do that, then immediately we can say that this quantity is just 1 minus 2 times 1/6. So this is greater than 2/3. So it really does mean in this setting that the plurality vote is overwhelmingly agrees with one direction. So if this was an election, that there is definitely a winning party, like not anything close. And that's important for us. In fact, that's all we need in order to show that g of f is a linear function. So how do we do that? Well, okay, so before how we do that, if we prove now that g of f is linear, then we are done. Why? Because the distance, because we know that this equation holds, that's what we just showed, and g of f is an element of all linear functions, so we can just choose. So this is the same argument we said before, only a bit like more formally, that it's enough to look at one particular function, and this is how we can see the right direction. Okay, so how do we prove that gf is linear? Yes.
Shouldn't it be inequality, like the last equality, because it's just one function?
You're absolutely right. Yeah, this definitely has to be an inequality. Thank you. Right, exactly. That's exactly the point that I was trying to make. Right, I mean, it might not be the best function, but it is a bound. Right, so this is exactly why this is a lower bound. Thank you. Okay, so we have the claim here, and we can assume that the function is not overly corrupt. It's like the number of bad triangles at most is 6, and I want to show that g of f is entirely linear, and we'll do it using this dual view. Instead of arguing that we can reconstruct the coefficients of the linear combination, we just argue that for every x and y, we'll have gf of x plus y is equal to gf of x plus gf of y. So this is a really nice trick. The first time I have to confess that the first time I saw this, I was really confused, and so I want to do it like in reverse to the way that I learned it, just because it made a whole lot more sense to me. So let's try to do this trick, and I think there are two nice ideas. So the first idea is the triangle which strikes back, and what do I mean by the triangle? We'll want to argue the following thing: how can we prove that the function is linear? So the idea is, let's consider this auxiliary variable, like a variable that you don't really need it, but we can kind of like argue about it. And suppose that we can say, well, I have a function gf of x, and there exists this vote which would lead me to the value of g, which would correct to gf of x. And suppose that for the exact same z, I'll have another correction relation like that. I can derive y from getting these two terms. And also here, for gf of x plus y, I can derive this vote that contains this thing. So what's happening? Suppose that somehow I have this magical z which satisfy all of these three conditions. What would happen? Well, something nice would happen. It would mean immediately that g of f is linear. And why? Because if we'll just write down this equation, g of x plus y equals g of x plus equals g of y, and we'll see all these terms. So the auxiliary guy, this one would cancel with this, and this would cancel with this, and we'll just have the linearity constraint, right? So it's kind of like a triangle inequality kind of thing with like that each time something would cancel. So this is a nice trick. It means that we're kind of like referring to this linear structure of self-correction, and in order to prove that something is linear, we're showing that for any x and y that we fix, like we have this this z which would cancel out, and we can and then we're done. Like we just like this is just a fancy way of writing that linearity holds, but we do it using a statement regarding the existence of this z. And now, how do we show that this that such a z exists? So this is a nice, the second trick, which is really nice. So we'll do it using the probabilistic method. So instead of like saying, I'm going to show you what is this x, I'm just going to show you that like the probability that such an x exists is, it's not zero. So let me show you what I mean by that. So first of all, we do this thing. So look at this statement. Might look a bit confusing, but what is this? We just want to prove this claim. So I'm just like writing it down, but I'm using z now as a random variable. Okay, so I just like copied this condition using z as a random variable instead of y. And the nice thing is that when I write it, then from what we proved before, we already have this equation here, right? So I can immediately write this thing down, and we know it's equal to 2/3. Right, so far I'm doing absolutely nothing. I'm just taking something that we know holds for every y, and I'm now saying, well, let's do it for a random y. So I just literally took this equation and changed the name of the variable from y to z. Nothing happens here. And then I'm doing the exact same thing, but with respect to y. I mean, why not? But, I want to be in this situation, and it's kind of exactly what's happening, but it's hard to see it. So I'm just doing here a change of variable. What I'm doing is I take each instance of z and I write instead z minus y. And the reason why I did it is because this is exactly the second equation that we looked at. And I will also, as you can probably guess, do the same thing with respect to x plus y. So I'm writing the equation for x plus y just like completely syntactic way, and I change the variables so I get exactly that. And now what is happening is kind of like a cute thing. So like, let me try to draw it, and maybe it would be easier. So I want to find a z that works for all of them. So maybe let's look at the first guy. So I know that like there is, a third, like 2/3 are good, and 1/3 I don't know, right? But I have this for 3 conditions. So even if I try to take, so I have like 3 of these, 3 of these circles, and even if they minimally intersect, and let me have this one as well. Looks like lots of peace signs. So the point is that we know that because this is strictly greater than 2/3, strictly greater than 2/3, and strictly greater than 2/3, it means that the bad part is strictly less than 1/3, strictly less than 1/3, and strictly less than 1/3. And so it means that there has to exist one point which touches the green part, like the good part of all of these points. Right? Just like a pigeonhole kind of thing. Yeah. And that's the entire trick. So, to kind of to summarize this, what happened here before I take some question is we have this like 2 nice ideas. One idea is that we're pushing self-correction once again, and we're considering here these like auxiliary variable that, and so we have here these 3 triangles which cancel themselves and give us using the existence of a z. And then we prove that this such a z exists just by talking about the probability and showing that this is not an empty event. So that's the last trick, and here we are done with the technical material, and I now have 10 minutes to answer questions and to tell you some nice, cool things. Any questions?
I have a question. So I didn't quite get, so have we proved that this function g of f is linear with some probability, or are we just using probability in our analysis and all claiming that gf will always be linear?
Yeah, so that's a good question. So we are proving that gf is a linear function, period. There is no randomness whatsoever, but we're doing it using an instance of the probabilistic method, which is a kind of a cute idea. It tells you that, in order to prove the existence of something, you can just say that it exists with probability non-zero. And just the nature of things is that we're talking about non-explicit constraints. Sometimes it's like, really hard to find objects, but they exist in a vast amount of, like, let me give you an example which I like. Like one of the most important goals in complexity theory is like to prove, that P is not equal to NP, right? Like we want to show that there exist hard problems, and one of the most promising approaches towards that end is like by showing, is there a Boolean function which requires this exponential size circuit? And now this is, such a big problem. If we solve it, we get like $1 million from the Clay Institute, and arguably this is maybe the hardest way to make $1 million. But never mind. And like the reality is that if we take a random function, then by simple counting argument, we see that a random function requires exponential size circuits. So like the absolute vast majority of functions requires really large circuits. But when we try to find an explicit circuit that we can write down, which requires large circuits, and we are completely miserable. And same things we see with like, expander graphs that like, it's hard to build them, but the random graph would have this nice property. So the probabilistic method is kind of like telling us that sometimes we have objects which, finding the structure is extremely hard, but because it's a very common phenomenon in random structures, then it's enough to do these existence claims. So that's the idea of the probabilistic method. By the way, this type of things, just going back to the first lectures and the crisis and the foundations of analysis and stuff like that, this whole question of whether we are fine with these non-constructive proofs. It's like in the beginning of the 20th century, there was a huge debate about it. But I think that by now, the entire community is quite comfortable by saying, well, you know, there exists a Z. I can show you that there exists a Z, but for the life of me, I cannot write down how it looks like. Any other questions?
Tom, hi. I'm just wondering if, like in this last piece, if you would draw this last three equations that you outlined in green as triangles kind of glued to each other, would it be something nice?
Yeah, I mean, yeah, that's a fair point. I mean, but you're right? I mean, like in some sense, they would just be, you know, infinitesimally close to covering a circle, but short of it. Yeah.
No, but maybe it would be something like what's that, like scene with four triangles at the side, like what's it called? Like a pyramid. Like you see, you have x plus z and z. Then you have y, z star, y, blah, blah, blah. Then you have the third one, but then the first coordinates, they also kind of are glued to each other.
That's interesting. Yeah, it might. I'll give it a thought. It might make for a nice illustration. Thanks.
I think you mean a tetrahedron, right? So
yes. I just
Z to be the peak of the pyramid, and then x, y, and x plus y to be the base.
It seems like something like that should happen. Oh, okay.
Yeah. I mean, mostly convinced, but let's like check it offline. I think it's a cool way of thinking about it. Thanks.
I have a more general question. Like at the beginning, you said that the class of linear functions was essentially like a Hadamard code, and how would like this theorem translate in like coding theory, or is there a kind of like translation in?
That's a classic question. So, so what we actually showed in this theorem is that the Hadamard code is locally testable. So it means that you can check whether you, so you know, linear functions form this code which is called Hadamard. So you can take any message, you know, and encode it using the Hadamard code word. And now suppose somebody is giving you something which is claimed to be a Hadamard code word, and you want to know, is that a true Hadamard code word, or is that something which is epsilon far from being Hadamard code word? So you can run this exact test and you know, and deal with that. So that's a way of doing that. And in some sense, more generally, like you see that, you know, so we had this linearity testing. And what we'll do with this linearity testing is we'll build a PCP where we encode everything by the Hadamard code word. And then somebody would give us a PCP code, which will be this Hadamard code word. And we'll run the linearity test in order to check membership in Hadamard. And after we know that this is a valid encoding, we can use all of the beautiful symmetry of like linear function and triangles in order to just check the problem locally. And because Hadamard has an exponential size, this would lead to a very huge PCP, which we later try to optimize. But in some sense, this encoding by the Hadamard code is what will take our, you know, free coloring that we want to check really efficiently. This is what we would endow it with this beautiful structure that we can, you know, admit this local to global. And we can also do things which we will do, like correcting a point X by saying, let's pick a random point R and just look at f of x plus r and f of r, subtract them, and then I can recover a point x, even if this point is corrupted or this point, you know, it's part of an invalid proof. Yeah, so we'll do this next week very explicitly. So this is where I'll remind you of that, and we'll deal with that. Yeah.
Thanks.
Okay, so just to quickly summarize, so I won't go over time. we had a proof. It persisted in these like 3 steps. The first step that we did, we kind of said that the number of bad triangles is captured by a distance from one particular function, the plurality vote. We show that plurality vote implies an overwhelming majority, and in that case, the plurality vote is actually a linear function, and that was the idea of the analysis. And you'll see that tomorrow in low-degree testing, we'll have this exact same structure, but with a much more interesting problem than just linear functions. And you'll see polynomials. I have to say, this is my favorite mathematical objects in the world. And in fact, we'll start the lecture tomorrow by me telling you about the magic of polynomials and why I love polynomials so strongly. So just to conclude, so I really hope I'm not going to annoy and make you angry, but we did all of this hard work, but there exists a proof, an alternative proof for the theorem we showed, which is like, I don't know, 5, 6 lines, and I could have covered it in maybe, I don't know, 7 minutes. So why did I take you through this, excruciating 90 minutes of a proof? So just let me say a couple of words about it. So what I actually stated here, this is a Fourier theoretic proof. And in some sense, you take some kindergarten level of Fourier analysis and you just apply it, you just write down the quantity that you want to analyze, you write it down in the Fourier expansion, you apply, simple identities like Parseval inequality and the convolution theorem, and you're done. So this can be really done in 5 to 10 minutes. So why did we go through all of that? It's not because I want to inflict pain on you. So there are 2 answers to that. There is one, decent answer and one much better answer. So the first answer is that yes, this analysis using Fourier, it only works for F2, whereas what we did in a much more general setting of any finite fields and in general, and you'll see that it extends to a very large thing. You can even further extend this proof to work over 1 billion groups and even beyond. And that one is kind of tailored to the setting of the hypercube. And the other reason, which is much better one, is that I think that mathematics often suffers from too slick of proofs. So when I saw this Fourier proof, and I actually saw it before I saw the combinatorial analysis that we did, at least me, I kind of went step by step, and it all makes sense, but I have zero intuition regarding why this magic happened. And over time, during the years, I sat over coffee with some of the authors of this paper, and even they admit the intuition is kind of it's very vague. You just write things up and they work out. And I think that it's often tempting when we're trying to understand proofs to go with the slickest, shortest proof. But sometimes it doesn't give us any intuition. And for the love of God, I wouldn't been able to come with this proof if I didn't know that somehow Fourier analysis is the right thing to do in this setting. I mean, once you know that is the right thing to do, then it's completely elementary, but why? Whereas what we've done is something that, even if it's first time, it's a bit confusing. If you go over it twice or 3 times, then you'll see that it's all straightforward. There's this approach and you make concrete steps for it. And this is why I think this type of approach is much more robust. In fact, it would prepare the road for low degree testing and for others that we'll see. So it's much, I think it's more, it has better pedagogical value. That being said, it's really nice, slick proof, and I encourage you all to spend some time seeing that it is a really nice idea, which is kind of inspired by Roth theorem, and it's a nice thing to do. Okay, so this is all I want to say. I'm running a bit out of time, so I'll pause. I'll stop the recording now.